So the next section we're going to look at is vector components. And what we're looking at with our vector components is the idea that we can take any vector quantity and we can break it up into a vector sum of component vectors. So what that means is we're going to take a vector quantity, and instead of looking at that one, we're going to look at two other vectors that basically add up to what the vectors that we're actually interested in. Now the reason why we want to do that is once we have those vector components, we can deal with those vector components independently of each other. And if we're doing them independently of each other, what that's going to, or just going to simplify our calculations, because then we can say just deal with the horizontal motion, and then we can separately deal with just the vertical motion. And so we looked at this a little bit with the river crossings, where you could look at just the distance directly across the river, or then the distance that was being carried downstream. We could do those calculations separate from each other, and that simplified things a little bit. And that will for these problems then as well. So if you look at this first one here, we have a ball that's being kicked upwards with a velocity of 15 meters per second at an angle of 30 degrees from the horizontal. And what we're going to do is we're going to split that up into two components, one vertical and one horizontal. So the actual path of the ball is going to go along something like this. So it'll be 30 degrees from the horizontal. So this will be a 15 meter per second vector. And that's the actual path that the ball is going. So what we're going to do is we're going to take two other vectors that add up to this vector but aren't along this path. So the first one will be the horizontal. And so just we'll look at the horizontal motion. And so we'll draw an arrow in here going up along just the vertical motion of this. And we'll call that the velocity, but only in the x component. And then we'll do a second vector, which is then going to head straight up. And it has to meet kind of where this one ended there. And so this is going to be then our velocity, but in the y component. And so what we see here is our resultant vector, the place where the ball is actually going, is going to be along this blue line here. But we're doing a vector sum, a horizontal piece and a vertical piece that starts and ends in the same place. So it is going to be an equivalent vector. The reason why we want to do this then is now we can look at only the horizontal motion, and then we can separately look at only the vertical motion. And basically doing those separately is going to be easier than doing the 2D problems. It's basically turning a 2D problem into two one-dimensional problems. So if we want to find what Vx and Vy is, we can add our vector here, and then we have just a simple triangle. And so this angle here is going to be 30 degrees. And so we have one side, the hypotenuse, because the x and the y will always be 90 degrees from each other, so this always forms a right angle triangle, which is why we're picking those two vectors. And so with the hypotenuse and the angle, we can easily then solve for the other two vectors. So Vx is on the adjacent side, so we'll use cosine. So cosine of 30 must be equal then to Vx over 15. I can multiply the 15 to the other side, and so 15 cos 30 should be equal to Vx. And so Vx, if we calculate that out to two significant digits, will be 13 meters per second. Okay. I can do the same thing with Vy, but Vy is going to be the side opposite to the angle. And so for this one, we'll have sine 30 will be equal then to Vy over the 15. Multiply the 15 over again, so the algebra is the same for each. And then I get a Vy of 7.5 meters per second. Okay. And so remember then that the components can be treated independently of each other, and this is why we want to do that. So we can apply things like conservation laws, we can do net force equations, kinematics problems. When we can do all of those, now we can do them just horizontally and vertically. That gives us basically two one-dimensional problems that we can use then to more easily solve some two-dimensional problems. So looking at an example here, we have one of those hanging weight questions or hanging mass questions. We've done those before. So for this one here, we have a mass of 30 kilograms suspended by two wires. Now what's different about this one here is if I do the vector triangle, I'm not going to get a right angle triangle, which is going to make this one more difficult to solve. So what we're going to do instead is we're going to take these three vectors, and remember I have a T1 pulling in this direction, I'll have the T2 pulling along this line, and then force of gravity, of course, pulling straight down. So what we're going to do with that is we're going to basically just set up a table with two columns, an x component and a y component. And so what we'll put in there then is we'll do an x component to all of those vectors, and then we'll do a net force equation for those, and we'll do a y component to all those vectors, and then do a net force equation for all of those. So if we just kind of put our two columns here, so we'll do an x component and a y component, And the x component is just the horizontal component, and the y component is the vertical one. And then we'll look at our three vectors. So if you look first of all at our force of gravity, now force of gravity just goes straight down, and so that's going to be a fairly easy one to do because it doesn't have any x component. So because it's vertically straight down, the x component is going to be 0 because there is no horizontal motion to it, and my y component then is just going to be m times g, or 30g in this case because it's a 30 kilogram mass. If I look at T1, that's also going to be a fairly easy one because T1 is all horizontal. And so this one here is going to be all x component, but no y component. Now one thing we haven't done yet, but we need to do, is we need to set a positive and a negative direction in each, because these are vectors, of course. So I'm just going to take this to be my positive horizontal direction, and this to be my positive vertical direction. So to the right and up. Now again, that's arbitrary. You can pick whatever you like for those, but I'll just pick those. Generally speaking, going to the right and up is what we generally pick to be our positive directions. But you can flip that and that'll be fine. So in this one here, all of my T1 is in that y component. So I can actually just use the same variable for that because all the force from T1 is going in that horizontal direction, but it is opposite my positive direction, so I do need to put a negative in there. And again, there's no horizontal component to that, so that one's going to be 0. Okay, and so those ones are going to be fairly straightforward, and we can do those fairly quickly because I get 2 of my components going to 0. Now T2, on the other hand, is going to have both components because T2 is coming up at an angle. And so T2, at the angle of 20 degrees, that is going to have both an x and a y component. And so my x component is going to be along this side of the triangle, so I can draw that one in. And then my y component is going to be on this vertical side of the triangle. And so that'll be my T2 in y. And then I can, of course, have also T2 in x. And so then I can use the same trigonometry I did before to solve for each of those. So for my x component, my T2 in x is going to be on the adjacent side, so I'll use cosine. So cosine of 20 is going to be equal then to the x component of T2 over T2. That means T2 in x will be equal to T2 cos 20. Now I don't know what T2 is, that's what I'm looking for, but that's going to be my T2 just in the x component. And then I can do the same thing with my y component, but now we'll use sine because it's on the opposite side then to the angle. So that's going to be sine of 20 equals T2 in y all over top of T2. And so then I'll get T2 sine 20 equaling T2 in that y component. Now what this is going to allow me to do is it's going to allow me to do 2 net force equations. I'll do one net force equation in the x component and one net force equation in the y component. And that'll give me then 2 one-dimensional problems that I can use then to solve for each of these. Now I know what m is, so I know what the mg is going to be here, just 30g, and so I'm going to solve for my y component first. Now the other thing to remember is that my net force is going to be 0, both in the horizontal and the vertical plane, because the object's not moving. So if it's not moving, it's not accelerating. It's not moving horizontally, so my net force in x is 0, and it's not moving vertically, so my net force in y then is also going to be 0. So let's start with our y component. And we'll do then just a one-dimensional net force equation. Now remember too, up is my positive direction, and my T2 in y was up, and so that's why this is a positive value, whereas my mg, and I haven't done that, but I should, is going to be a negative value because that's going to be down. So when I do my net force equation y, I have my force net, and that'll be 0, and then I'll take my T2 in y, which will be T2 sine 20, and then I'll subtract 30g, which is my mg. Okay, my force net was equal to 0. Now I can add 30g to both sides to move that to the other side. So 30g equals T2 times sine of 20. If I divide both sides by sine of 20, that gives me T2. So I get 30g divided by sine 20, and that's going to equal then my value of T2. And so if we calculate that one out, we get 860 newtons. Now we only have 2 significant digits, and so then I'll just go to 0.86 kilonewtons for my T2. So we'll just shrink this down a little bit to give ourselves a little bit of extra room. And then we can do the x component. Now we already have T2, so it'll help us with the x component. So for the x component here, we'll do the same force net equation. Now this force net equation will be then the negative T1 and then plus the T2 cos 20. So my force net, again, is going to be 0. Now my T1, which is what I'm looking for, I'll move to the other side. I can add that to both sides. And so what I'm left with then is T2 times cosine of 20. Now I already have T2 from down here, so I can use that value. And so T1 is going to be the 860 newtons times cosine of 20. And if you calculate that, we get a T1 value then of 809 newtons. And again, to two significant digits, 0.81 kilonewtons. Now you could also use scientific notation for that, but we'll just change the unit in this case. So when you look at these two values, T1 and T2 are both over 800 newtons. Now if we look at what it would be if there was just one single rope holding it directly above, that would be equal and opposite to the F of G, and so it would only need about 30 G, or less than 300 newtons, to basically have one rope holding that. And we see both of these ropes that are together holding it have considerably more tension in them. And the reason for that is because the two ropes are pulling against each other. So if I look at this T2, this is made up of a horizontal component going this way and a vertical component going this way. Now this vertical component here is the only thing that's counterbalancing the force of gravity. So the vertical part of this is that 30G. All of this horizontal part of it here, or this horizontal vector, is basically just counteracting then the T1. And so because these two ropes are working against each other in that horizontal plane, my final tension in both of those is going to be considerably larger. And the wider space those angles are, or the wider space those ropes are, and the smaller those angles are to the surface there, the greater the tension then is going to be in those wires. And so if we look at just as kind of more of a theory question here, if I have two ropes holding the same mass, so if we look at the vectors then that are required to hold each of these, so for the one with this moment there, I'll have two vectors pointing straight up, one for each of those ropes there, and then I'll have two vectors pulling against each other, and that'll then be equivalent then to the two tension vectors. So remember, the actual tension vector is going to be along the line like this, and I can break that up into a vertical and a horizontal component. And then the same thing along this line here, start to finish, so I have a vertical and a horizontal component. And for these ones here, the sum of these two vectors has to equal then the 10G, which is counteracting then the force of gravity, pulling straight down. However, I have these two horizontal tensions that are pulling against each other, and so that's going to increase then the tension in those ropes above what they would be if they were both heading straight up. So as I stretch those angles out even more, I do still have those net vertical components to the tension that are counteracting that 10G, but as I pull those ropes further and further out, what I'm doing is I'm extending then these horizontal components. And so I have basically more force acting against each other. So my net tension is still along this line and this one over here, so along the ropes there. But the sum of those tensions now have a much larger X component. And so the total tension in each is the sum then of the vertical and the horizontal component. So the vertical components are the same, but this one has much larger horizontal components, which means I'm going to see much more tension there. And so the wider you space the wires, the more tension you're going to have in the wires. The closer they are, the least tension you're going to have. And the very least tension you can have is if they're both vertically upwards, because then there's no horizontal force acting against the two wires, and so everything's just counteracting the force of gravity. Yep. So the last one we'll do is we'll look at what happens when we have our handles that are basically set up at some angle. So here we have a wagon that weighs 95 kilograms and it requires a force of 120 newtons to pull it along a flat sidewalk. And so what we're looking at here then is if we have just a box and we're pulling with a force of 120 newtons along the sidewalk, we should be able to make the wagon move at a constant speed. However, what we're going to do then is instead of pulling it along here, we're going to add a handle that's going up at 50 degrees. Now we still need to pull this 120 along that horizontal component because that's what's going to be required to move it in that horizontal direction. But what we're going to be interested in is what happens when we have a handle. So if we redraw this one, we'll take then just our level ground here, put a box. And then our handle then is going to be heading upwards at 50 degrees from the surface. Now, as we said before, what we need to have in order to move this is we need a force of 120 newtons along the direction of motion. So this is going to be a 120 Newton force, and if we pull 120 newtons basically horizontally, will make this object move at a constant speed. Now, if we were just pulling it here, that would be very inconvenient because you have to bend down a long ways to kind of pull a rope along here. So what we'll often do is we'll use a handle that allows us to pull on it from a higher vantage point. What that does mean, though, is that we're introducing then a vertical component to our force. Now, we don't really need this, so we're not going to be lifting up the wagon. Now, presumably, if you pulled with enough force along here, you could lift up the wheels of the wagon, but we'll assume that it stays flat. So really, all of this, all of this is actually just going to be a wasted force. So what we're going to be pulling with is the force along here. Now, 120 newtons of that in this direction will be useful because that's going to be moving it in the horizontal direction. But anything that we have in this vertical component is really just wasted force there. So it does mean that if we're using a handle, we're going to have to use more force than if we weren't using the handle, but it's more comfortable to pull it, and so that's kind of where the trade-off is. So here, if we're looking for the force that must be applied to the handle, that's going to be this force over here. And you'll notice that that's the hypotenuse. Remember that we always have a 90-degree angle between the x and the y components. And so I can use trigonometry then to solve for this one. And so I have the 120, I'm looking for the hypotenuse. Now we could also find the f of y, but we don't need to because we're just really interested in what's required to make it move horizontally, and then what force are we putting into the handle there. And so let's just maybe call this force net. As for this one here, we can use cosine for that. And so cosine of 50 is going to be then equal to that 120 newtons, which is then the adjacent side down here, all divided by the hypotenuse, which is my force net. Now you'll notice here the variable I'm trying to solve for is in the denominator, so I'm going to first move that to the numerator when I'm trying to isolate it. So I'll multiply that out to the other side. So I get force net equals cos 50 equaling 120 newtons. And now I can just divide out the cos 50 from both sides, and so my force net will be equal then to 120 newtons, and then all divided by cosine of 50. Now because I'm dividing by cosine of 50 will always be less than 1, and so I'm going to actually get a larger number, which is what I'm expecting, because I should always get a larger number for the force along the handle than the force along just one of the components there. So if I divide those two out, then I'll get 187 newtons. And that'll be then for A, the force then that must be applied to the handle in order to pull the wagon then at a constant speed. The next one then I can look at is B then. And so we can look at what is the coefficient of friction between then the wagon and the sidewalk. Now to do that, we'll set up a net force equation. Now we are moving at constant speed, and since we're moving at constant speed, the net force is going to be 0. And so we'll have to include that in our net force equation. So we'll have then a force net, which we know is going to be equal to 0. Now that'll be equal to my force applied. Now I am just going to use the horizontal one. I don't want to solve for a two-dimensional motion problem if I don't have to. And what I'm looking at here, when I look at my second force, I'll have then a force of friction applied here. Now the actual applied force is being pulled along here, but I know that the one that's counteracting the force of friction is only this. So my force of friction is only horizontal because it's traveling horizontally. So the only force that I need to include with that net force equation is this x component. This doesn't affect the force of friction at all, and so because it's in that different component, I don't need to account for it here. So my force net then will be that force applied along just the x component, and then minus the force of friction. My force net I know is 0, so I get 0 equals, now my force applied is 120 just along that component, and then I have mu mg for my force of friction. And so I can take the mu mg to the other side. Now mu is what I'm looking for, so that's my coefficient of friction. I have a 95 kilogram wagon, so that'll be my mass, and then I have g all equals 120. So I can just divide that out, and so mu will just be 120 newtons divided by 95 kilograms times g, and so I get for my mu value there 0.129. Don't forget those have no units, and that'll be then my coefficient of friction. And then for the last one, we can look at what is the acceleration if a force of 200 newtons then is applied to the handle. Now if I'm applying a force of 200 newtons to the handle, what I'm going to be interested in is what does that make my x component. So in this one here, we'll redraw the handle. Now my handle is still at 50 degrees from the surface, but instead of 187 newtons, I'm going to put 200 newtons along here. And what we're going to be interested in then is what does that do to the horizontal component. Now I still have a triangle here. Now I'm not interested in the vertical component, but we'll just draw that in to complete our triangle there. What we're going to be interested in is this x component. So we want then this force applied now in x. So I need 120 newtons along there to keep it moving at a constant speed, which gives me 187 in the on the hypotenuse. If I increase the hypotenuse, I should increase my force in x then as well. This is again just a trig function. So now we have cosine 50 is going to be equal then to force applied just along the x component all over 200. So 200 cos 50 is going to be equal then to that force applied now just in that x component. So if I just carry that one through actually into my net force equation, I can do force net, which is now going to have an acceleration to it. Now if I look at this, I still have this force applied in x. Now I will still have the same friction force here, and so I will still account for that friction force. Now I could use my mu value for that, but I know from here that my friction force, and I should have a mu here, mu 95g is equal just to 120. And so for my force of friction, I can just put in the 120, and that would be a little bit simpler. We could do the mu times 95 times g, but that of course just equals 120 again. So my force net, I have 95 times my acceleration, which is what I'm going to be looking for here. My force applied in x is that 200 cosine of 50, and then I'll subtract 120 newtons, which is my friction force. So I can get my acceleration, will just be all of this divided by 95. Divided by 95 on both sides. So over here. And so my acceleration then is just going to be 0.0901. And that'll of course be meters per second squared. Okay, and so when you're doing these types of questions, always remember that when you are pulling along a handle, the force along the handle is always going to be greater than the force required to just move it along. And again, you have a trade-off there. So it's more comfortable to pull on the handle because it raises the level at which you're exerting your force. And so it's much easier than bending down to pull it level. But the trade-off is you have to actually pull it with more force, because as you raise that handle up, you're going to get more wasted vertical force. And the steeper the angle of the handle, the more wasted force you have. The lower the angle of the handle, the less of that wasted force than you have. So always remember you have that trade-off there, and make sure the hypotenuse when you do your calculations is always the longest side, of course.